All right, I'm Rocco with MIT Lincoln Laboratory, and I am going to talk about the VITA 100, but the evolution from VITA 65. We learned a lot with VITA 65, and we're leveraging what we've learned in VITA 65 into VITA 100. I'm editor of VITA 65.0.1 and 100.0 and 100.1. All right, so I'm going to skip over the outline. So we're getting, in addition to getting input from VITA, we're getting input from other standards organizations. SOSA, or Sensor Open Systems Architecture, the hardware group there, is giving us input. They actually passed on a set of requirements to us. There's a host hardware open systems technologies community, and then the Army has the CMOS standard, and they're actually giving their input through SOSA. So there's a fairly large community. It's not just VITA that's involved in getting input. I'm going to skip this. And overall, we're getting about a factor of 8 improvement in the bandwidth between a plug-in card and the backplane. 2x of that approximately is due to from pins doubling, and depending whether it's 4-pair or 6-pair, it's a little bit less than 2x or a little bit more than 2x. The baud rate is going up by a factor of 2, and then we're getting another factor of 2 by being able to have PAM4, which gives us 4 levels instead of just 2. That enables 2 bits per baud, and so overall, we can handle things like 100 gigabit Ethernet over a single lane, or 400 gigabit Ethernet over 4 lanes, or what we call a fat pipe in both VITA 65 and VITA 100. Skip that. Here's a summary of the slot profiles in VITA 65 over time. When we first did it in 2010, VPX had already been out for a few years. VPX came out around 2007. The COTS suppliers, I was actually with Mercury at the time, but we had products already in the works with VPX. And so what ended up happening is we sort of standardized what we were doing in a sense, as opposed to starting from scratch. And so what we're doing with VITA 100 and QMC is very different, because we're starting from scratch from just the requirements. And you can see in 2010, we had a total of 36 slot profiles. The column on the right there is the totals. And then 2012, we added some more. 2017 is when we really started doing optical and coax in a big way. And so then we added 34. Then 2019, we got a lot of input from SOSA. We added some slot profiles there. And that's also when we reduced the number of user-defined pins to just almost completely getting rid of them. So we added another 11 there in 2019. And then since then, we've only added 1. So we ended up with 93 slot profiles in VITA 65. And I'll show you, I've got the counts for what we're currently planning in VITA 100 also. And I expect that VITA 100, we'll probably add a few over time, but I don't think it'll be anywhere near the growth rate of VITA 65. I expect it to be more like the growth rate from 2019 on. Like if you see, we just added 1 over a couple of revisions. Here's the family, a little bit more zoomed in. This is a family of 3 U slot profiles. The first 4 are for compute-intensive things with RF and optical apertures on the first 3. And what we do is, as we reduce the RF and optical apertures, we're adding more expansion plane, more data plane. And then with the third one there, 10.2.3, we're adding USB 4. And then with the last one, we added more USB 4 and expansion plane. And then the next 2 are more for I/O-intensive applications, more like a conventional SBC. So there we've got a lot of expansion plane, and then we've got mezzanine mapping. So the pair of slot profiles there, 10.2.5 and 6, are the same except for the mezzanine mapping. The one on the left is for QMC, and then one on the right is for XMC. So the QMC one is bringing out the I/O pipes that were mentioned earlier this morning. And then the last slot profile is, if you've got a lot of system specific stuff that won't fit on an XMC, we've got a slot profile that's mostly user-defined. And the goal here is push all the user-defined stuff in one place so that the other stuff can be upgraded and over time and have multiple suppliers for it and so forth, all the good standard stuff. Let's see, I will skip this one. I'll talk about this one a little bit. This on the left is it's one of the current VITA 65 slot profiles. It's intended for IO-intensive SBCs. It's got an XMC mapping. On the right is the sort of equivalent with VITA 100. We've obviously got more IO. We're bringing on the XMC mapping. We're bringing out the more single-ended pins, essentially the same as what the 6U is in VPX. And then the other thing that's going on is we're migrating to USB 4. So things like video, now the plan is to just use USB 4 for that. So there aren't as many different kinds of interfaces with VITA 100 because we're leveraging USB 4 for a lot of the I/O, those sorts of I/Os like displays. Let's see, I'll skip over this. Here's the family of 3U switch slot profiles. The first two are using the 4-pair connectors. One has an aperture, one doesn't. And then the next two use the 6-pair connectors. The slot spacing goes up to 1.2 inches, but we get a bunch more I/O. And it's worth the trade to take a little bit more space for the slot to be able to get more both data plane and control plane ports out to the plug-in cards in the chassis. Here's the family of 4U proposed 4U slot profiles. Again, we did a similar thing where we've got a large aperture on the left, and then a smaller, and then smaller. Here, since we've got so many more pins, we've got the XMC and QMC mappings are right there, and the I/O intensive type applications can take advantage of the USB 4. So we only need 4 slot profiles for this family, and then there's the one that's mostly user defined for people that have a lot of just custom stuff that they need to fit in. And we'll skip over. Here's the 4U switches. We've got one 4U switch with an aperture and 4-pair connector, and then the one on the right there is got the aperture. And given the additional pins, we didn't see a need to have one with and without aperture, so we've just got 4-pair and 6-pair versions. On the left is that's a 6U VITA 65 slot profile, which is comparable in capability. Actually, the 6-pair 4U can handle more I/O than the 6U VPX. And then we've got a family of 6U slot profiles, and this is showing and the way we built up the 6U ones was we just took 2 copies of the 4U slot profiles and stacked them, except for the P0 connector, which is the utility plane. So we've got decreasing aperture sizes again, and then the 3rd and the 4th ones there have provisions for 2 sets of QMC mappings and 2 sets of XMC mappings. And then we've got the one for system specific, basically all user defined. And then we've just got 1 switch slot profile. And then here's a summary again of the slot profile. So at the top of this table, you can see the 93 VITA 65 slot profiles is 63 in 3U, 30 of 6U, and then down the table on the bottom is showing what our current plans are for VITA 100. We've got 7 payload, 4 switch, and 1 miscellaneous. The miscellaneous one is for driving radial clocks and supporting things like GPSs. So that's a total of 12 versus 63 for OpenVPX. And then 4U, we've got 7, and then 6U, we've got 6 proposed. So in summary, we're increasing the bandwidth between plug-in modules in the backplane by a factor of 8. Slot profiles in early versions of OpenVPX were driven to some extent by the product plans of members. The 2019 version was the last version to add more than one slot profile, and that was driven by things going on in both VITA CMOS host and SOSA communities, and SOSA was a strong influence in that. And then VITA 100, we're proposing a family of slot profiles that build on each other, and we're taking advantage of the 6 pair going to 1.2-inch slot pitch with 3U and 4U to get a lot more I/O for switches. And the other thing I'll mention is in the 1.2-inch slot pitch, we're probably going to go to a larger fiber connector that can support 4 MTs. That's it.